Hey guys, so for the past couple of weeks, I've been working on a new shoe design, it's also design, and I've been building circuits and schematics for a PCB board that I just purchased. And I also created nodes for the sensors that I put on the robot, and that's what I want to go over today. So that's the pelvis that I sort of remodeled. Now it is similar to the first model from the front, except I added a little socket for the IMU. So how this works is we have this guy right there, which we can just slide out of there or we can just slide it back in. And we place the IMU right there. The wire sort of goes from the side right there and it slides up to this hole. So every wire that's coming from the leg servos is going to be going through this hole too, right? So the IMU wires just join it. It also makes sure that the IMU is right in the center of the whole base link and the whole robot essentially. See, let's start an analysis and you see how it's going to be right in the center from either sides. So this is what it looks like in person. We have the IMU wire, which is just going to go in from the socket right there, which leads into this door. Next up, we have the shoe. Now here I only changed a couple things. Mainly, I added one more FSR sensor since I noticed that having one was good to know if the leg was on the ground or not, but it's really essential to have two sensors to know if the foot is laying flat on the ground or not. Because imagine even if the foot is in contact with the ground, but it's sort of tilted, and the FSR sensor would go high, meaning it would believe that the leg is on the ground, and it would be, the heel would be on the ground, but it so wouldn't be, which means that it can't hold the whole robot's weight forever like that. So we need to have a way to know if the entire foot is laying flat on the ground or not. And one way to do this is simply by adding one FSR in the front and one in the back. So I'll sort of have a code or a logic where it sums up the readings from both of them. And it should have a mean, which should always brings back to if the foot is flat on the ground. If it's not, one of them is going to be too high or too low, and we'll know what's wrong with the foot if it's too forward or tilted backwards. Other than that, I added a new hatch for the Lidar sensor. As you can see, the same thing right there. We have this hatch that I just showed, or you could say a socket for the Lidar sensor, which fits in here, and then we have it on both sides, so we can know which leg has an obstacle up ahead, if any do. And we're gonna have the FSR below here. First, we have the sole right there. And then we're going to place an FSR right there. We're going to stick it on top. And we're going to have two wires running in from over here, which can go up the shoe because of this sort of channel I made. And for the wiring, right now, it is, of course, a bit messy in the breadboard. But this is my schematic for the PCB that I'm going to be using. And I did order it already, so it should be here in I think a week or so. And then I can replace the whole breadboard with this. So the PCB sort of goes on top of the battery socket. And till then, we're just gonna place the breadboard in the center since we don't have a battery to use right now anyway. We're using this plug right here, which has the socket bullet in, so you can just push it in, and there we go. For the connections, we have the IMU right there. So we have an SDA, SCL, 2.3 volts and ground connections from this wire. And then for the FSR sensors, we have an MCP3008 volt right there. And honestly, I don't even know how to explain it here. So we're just going to switch back to our computer. So how this works is we have a few connections from the MCP to the Raspberry Pi. So all of this you see here are the connections that go into the Raspberry Pi. This is probably not perfect or ideal since it's my first time making a PCB. So if you guys have any suggestions or something that I should work on, just leave a comment below. And On the other side, we have the channels. So each channel is each FSR sensor we're going to connect. And these are the header pins that we're going to have on the PCB board. So how this works is you plug into pins from each FSR. One of them goes into the power side, and the other one reaches a resistor. Right now it says 10 ohms, but I'm probably going to change it to find the best one. Most likely 1K ohm. So at this junction, one end goes to ground and the other one goes to channel 0 or channel 1. Now, how all of this is going to wrap in the code is that we're going to have nodes of every sensor here. So we're going to have a node for the left leg LiDAR sensor, one for the right leg, the IMU, and all the FSR sensors. And they publish all the data and all the readings on a topic, each topic for each sensor. So if anyone doesn't know exactly how it works, so basically imagine a notebook and you have two people. You have a publisher and you have a subscriber. So imagine the publisher is writing on the notebook and the subscriber is reading whatever the publisher is putting down. Now, in this case, our publisher is the sensor because it's giving the data and all of its readings, which it publishes on topic. A topic is the notebook in this case. And a subscriber is going over whatever is written and uses that data to sort of decide on what action it has to do. For example, if the robot states that there's an obstacle detected about 0.2 meters in front of the left leg, so it's going to go up to the topic and the subscriber is going to see it and it's going to go, we should go right since the object is slightly towards the left. And then the whole robot is going to start going towards the right. One important thing about this is that the subscriber can only read the data published in exactly that moment because the topic can't store data in any manner. So that's my thinking so far. So if a publisher is releasing something onto a topic, but the subscriber hasn't been subscribed yet or the node hasn't started yet. So when it does start, it can't go over the readings of the past. All it can do is get the new readings, which the publisher is producing at that moment. It's to make sure there's no latency and to make sure there's no lag. Since if the publisher is working on basis of the data it received or the data that was published 10 seconds ago or 20 seconds ago, it's going to be making the robot really laggy and it's probably going to break eventually because it's working on data that was released a while ago. So imagine in case of an IMU, which is going to be way more serious because it needs to be super fast. Imagine the robot is falling up ahead and the publisher didn't catch up on that data because it was so stuck reading data from a minute ago. It couldn't process the data in the moment and the robot just falls up ahead. And a minute after it falls, it tries to get back up, lean backwards or something, which is not going to work, obviously. So that's why we create a QoS profile in when we code it. So it can only pick up the latest 10 or so data. I'm going to launch up all the files and all the nodes for our sensors here. And once it's ready, let's just check if we can read all the topics. So we have two for IMU, but the first one is more, let's say, technical data, and the other one is something that we usually read and go over. Then we have the LiDAR for the left leg and the right leg. Let's try to run this code that's up there. So basically what this does is for the left leg here, if there is an obstacle lesser than 0.2 meters to the sensor, it's going to send a warning saying that there's an obstacle up ahead. So right now you see there's no warning at all, right? But if I bring my hand super close to it, you see that pop up. You see so many of them because it pings one for every time it reads from the LiDAR, which we need the computer to actually do so we can have real-time data. And if the obstacle goes, it should know it's not there anymore. We're going to have the same logic for both of them. And instead of just a warning to us, it's going to be giving a warning to the actual system, the brain of the robot. so it can move accordingly. We're going to have a similar system for the IMU. You can see the data of the IMU right there. So right now it says 0, 0, 0 for the XYZ values, right? Now, if I make the robot sort of fall forwards, you see how the X value goes up? And say if it were to fall backwards, the X value goes back, and then likewise for the sideways div too. And when it's back to sort of the center, it's going to be somewhere around 0, plus minus 2 or 3. That's how we know it's actually in the center and it's balanced. I think that's about it for today. And I am going to be working on the top part of the torso for the next couple of days. Once I'm done with that, I'm going to get the FSR sensors in the shipment by tomorrow. So I'm going to place both the soles of the foot right there. Once I have that done, I'm going to make sure the circuit works well. I'm going to create nodes for FSR sensors, which I haven't yet. And once I have the 4 parts of the torso ready, I'm going to stick that right on top of our robot. And we're going to run the first test. What this test does is it's just to sort of see if the physical aspect of the robot is actually realistic and if we can even make the robot move. So if the robot is falling backwards, it should take a right step back to prevent the fall, lean its torso forward at the same time. And then once it balances off at this position, it's going to slowly take left step back and come back to its new position, which is a step back from where it started. Once I have a good check on this and once I know this works, the next thing is I'm going to make the robot slightly fall towards the front and right, like northeast. And then the robot has to take a right step forward, of course, and it also has to use its yaw axis right there and then move its legs forward so it can go towards the side. And that's how I want it to balance. Of course, the other leg is also going to have to bend just a little bit. And once I have these two checks, once I know that it works perfectly, I can switch it all back on ASIC Sim. And then we can run the final test before we move it on ASIC Lab for the training. And I'm going to spend maybe the next couple of months learning how to use ASIC Sim and Lab, training it, uploading the model back onto Spookey. Yeah. All right. See you guys later.